I want you to do something for a second. Wherever
Yeah.
you are right now, just look down.
Right.
Yeah, just look at the floor. Look at the solid ground beneath your feet. I mean, feel how stable it is, right?
Yeah.
How impossibly dense and permanent it all
It
seems.
feels very permanent.
It really does. But now, I want you to try and imagine that exact same solid matter, literally everything making up the foundation of the Earth you are standing on, as it once was, which is, well, a chaotic, swirling cloud of incandescent glowing gas.
Yeah, it requires quite the mental leap. I mean, moving from a hot, formless solar nebula to the highly structured, solid rock of a terrestrial planet, it involves crossing some pretty profound physical thresholds.
It's basically the ultimate origin story. And the entire transition, how that hot gas literally condensed into the solid materials that built our world, it's something we thought we had mapped out.
We really did.
We did. But an international team led by the Institut de Physique du Globe de Paris, alongside ETH, Zurich, and Sorbonne Université, they just published a study in Nature that kind of shatters that old map.
It does. It completely tears it up.
Right. We are talking about a complete rewrite of the foundational moments of our solar system. And that is exactly the mission of our deep dive today.
Absolutely. And, the scientific term for this transition is condensation.
Condensation, okay.
Right. And for decades, astrophysics and cosmochemistry relied on a very specific framework to explain how the first solid minerals emerged from the solar gas.
Right.
And that framework was rooted almost entirely in thermodynamic equilibrium. The prevailing assumption was always that planetary formation was a highly orderly, gradual process.
So looking at the old thermodynamic model and the sources here, the math actually looks perfectly elegant.
Oh, it is, on paper.
Right, on paper.
Yeah.
It basically posits this early solar nebula as a giant slow cooker. You start with a blistering hot environment, and then the temperature drops by fractions of a degree over millennia.
Exactly. Very slowly.
And because it is cooling so gradually, the cosmic ingredients have time to settle into perfectly predictable, mathematically ordered layers. It's like a perfectly baked souffle. So my question is, why abandon a framework that makes so much theoretical sense?
Well, the mathematics of equilibrium are elegant on paper, like you said, but they fail the reality test.
Oh, really?
Yeah. In physics, thermodynamic equilibrium requires one crucial ingredient above all else, and that's time.
Okay, time.
Right. If the temperature drops incredibly slowly, the gas and the forming solid grains, they have the thermal energy and the time to constantly interact. They rearrange their chemical bonds and find their absolute lowest energy, most stable, crystalline state.
Makes sense?
It does make sense. The problem is when we actually analyze the physical evidence that survived from that era, the elegant math just falls completely apart.
Ah, so you are talking about the meteorite test.
Exactly.
The ancient space rocks that have crashed into Earth.
Specifically, we're talking about the chondrites, right?
Ah.
The ones that act as pristine time capsules from the dawn of the solar system. That's right. The chondrites are essentially the leftover building blocks. And the nature study focuses heavily on the three main classes of these meteorites. You have enstatite chondrites, ordinary chondrites, and carbonaceous chondrites.
And looking at the visual data in the study for these three classes, the physical differences are striking.
They really are.
Yeah, the enstatite chondrite is highly crystalline. It's almost this stark gray color.
Mm-hmm.
And then the ordinary chondrite is packed with these little round silicate pebbles or chondrules.
Right, the little spheres.
Exactly.
Mm.
And the carbonaceous chondrite is incredibly dark, super primitive, almost like a piece of oxidized charcoal.
Yeah, but the visual divergence is really just the surface level. The real issue for the old slow cooker model lies in their chemical makeup.
Okay, how so?
Well, when cosmochemists analyze these three classes, they find these stubborn, inexplicable differences in their concentrations of non-volatile elements. We are talking about the heavy hitters of planetary construction, silicon, magnesium, aluminum, calcium, and iron.
These are elements with incredibly high condensation temperatures, right?
Hmm.
Like they require massive amounts of heat to remain gaseous.
Exactly. Which means they are the very first materials to solidify as a nebula begins to cool down.
Okay.
And under a strict model of thermodynamic equilibrium, those non-volatile elements, they should have crystallized out of the gas in a highly uniform, predictable sequence.
Because it's slow cooker.
Right. A slow-cooling nebula should produce a relatively homogeneous distribution of those early minerals. But the meteorites we actually hold in our hands today are messy.
Messy how?
While one class might be completely depleted in certain refractory elements while another is heavily enriched, the ratios of silicon to iron or, magnesium to calcium, they just vary wildly between the three groups.
I see. So the slow cooker model mathematically insists these rocks should be uniform, but the actual rocks themselves are literally sitting on the laboratory table refusing to comply.
Yeah. Exactly. The rocks force the researchers to just abandon equilibrium entirely. I mean, if the early solar system was not in a state of slow, balanced cooling, well, the only alternative is to model condensation out of equilibrium.
Okay, but wait, let me just unpack this. If you abandon the slow, elegant cooling and you introduce out of equilibrium chaos, I mean, are we talking about a cosmic microwave here?
Kind of, yeah.
Like just violent dynamic movements? Because if the early solar system was purely chaotic, wouldn't that just create an infinite variety of random space rubble?
You would think so.
Yeah, how does pure chaos result in exactly 3 distinct, highly predictable classes of meteorites?
Well, that's the brilliant part. The early solar nebula was violently agitated, yes, but that violence operated under very specific physical mechanisms.
Okay.
We really have to look at the first 100,000 years of the solar system's life. This protoplanetary disk, it was not a calm, static cloud. It was a churning fluid. It was subjected to massive magnetic reconnections, friction from accreting matter, and most importantly, intense shock waves radiating outward from the young protostar.
Wow. Okay, so you have these localized regions experiencing basically catastrophic events.
Exactly. Regions of the gas were subjected to sudden, intense episodes of flash heating from these shock waves, and then that was followed immediately by extreme and rapid cooling.
Flash freezing.
Yes. The temperature would plummet so fast that the matter literally did not have the time or, frankly, the kinetic energy to follow the laws of thermodynamic equilibrium.
Okay, but at an atomic level, how does that flash freeze actually alter the rock?
Yeah.
I mean, if you instantly freeze a crystal as it's trying to form,
Mm-hmm.
doesn't it just fail to bind together entirely?
Not quite. The atoms become caught in what physicists call a kinetic trap.
A kinetic trap.
Yeah. In a slow cooling environment, an atom has the ambient heat energy to break weak bonds, move around, and basically slot into the perfect lowest energy position within a crystal lattice.
Like finding the perfect seat in a theater.
Right, exactly. But when the temperature plunges suddenly, that ambient heat energy just vanishes in an instant.
Oh, wow.
So the atoms are frozen in transient, higher energy structural configurations. They just bind together in whatever messy arrangement they happen to be in at that exact split second.
They are forced to lock arms with whatever atom is standing next to them when the music stops.
That is exactly it. Musical chairs at the atomic level. And because of this, minerals emerge that mathematically should not exist in an equilibrium model.
Unbelievable.
They are born entirely out of the rapid temperature drop. And here's the kicker. When the researchers ran their computer simulations modeling this specific mechanism, the localized flash heating and the subsequent kinetic traps of a flash freeze, the results were astonishing.
So the model didn't just produce infinite random space rubble.
No, it didn't. The chaotic model naturally funnels the condensing matter into only 3 major types of mineral assemblages.
Wait, really? Just 3?
Just 3. And those 3 assemblages match, one for one, the exact chemical profiles of the enstatite, ordinary, and carbonaceous chondrites.
That is mind-blowing. That completely solves the meteorite test. So the variations in silicon, iron, and magnesium, they aren't anomalies in a broken equilibrium model.
No, they aren't.
They are the direct, inevitable signatures of shock waves and flash freezing in the early solar disk.
You've got it. The diversity of our planetary building blocks was forged by hyperlocal flashes of violent heat and sudden freezing cold.
That completely upends how we view the rocks sitting in our museums. But what's crazy is that the nature study actually takes this mechanism a massive step forward.
It does.
Because this out-of-equilibrium condensation doesn't just explain space rocks. It literally explains the habitability of Earth. It explains the exact elements that keep you and me alive today.
Yeah, the implications shift from basic cosmochemistry to the origins of life itself. The out-of-equilibrium model solves one of the most enduring paradoxes regarding oxidized and hydrated minerals in the inner solar system.
Okay, let me make sure I'm grasping the old paradox here.
Hmm.
In the traditional slow cooker model, the entire inner solar system starts out at blistering temperatures, right? Like well over 1500 or 2000 Kelvin.
Yeah, temperatures high enough to literally vaporize rock.
Right, so at those temperatures, volatile elements like oxygen and hydrogen are just swirling around as gas.
Correct.
So my friction with the old model is this. If the environment takes tens of thousands of years to cool down, wouldn't those volatile gases simply dissipate? Or, just be blown out to the outer edges of the solar system long before the rocks were cool enough to capture them?
That is the exact problem.
Yeah, I mean, it feels like trying to pour water onto a skillet that has been sitting on a high flame. The
Hmm.
water just dances on the surface and evaporates instantly. It doesn't soak into the metal.
Exactly. In a slowly cooling, high-temperature environment, oxygen strongly prefers to remain in a gaseous state. It usually ends up bonding with carbon to form carbon monoxide. So, by the time the slow cooker finally reaches a temperature low enough for oxygen to theoretically react with solidifying metal grains, say down around 500 Kelvin, the chemical window has completely closed.
Because the gas is already gone.
Right. The gas is dissipated, or the solid grains have already grown too large and stable to absorb the gas efficiently.
Wow. So under those equilibrium rules, the building blocks of Earth should have condensed as completely dry, heavily reduced, rusted out husks.
They absolutely should have. And to explain the vast oceans and the heavily oxidized crust of the Earth using those classical models, scientists often had to rely on secondary delivery mechanisms.
Oh, right.
The prevailing theory required a massive bombardment of icy comets and volatile-rich asteroids migrating inward from the outer solar system.
Right, delivering oxygen and water
Yeah,
long after the terrestrial planets had already formed.
exactly.
A cosmic delivery service. I always found that theory incredibly convenient, honestly. Like, we couldn't explain how the oxygen got baked into the inner solar system naturally, so we relied on a deus ex machina.
Basically, yeah.
A fleet of comets just dropping it off later. Are you saying the new flash freezing model eliminates the need for that cometary delivery?
It does. The flash freeze completely circumvents the volatility problem.
Now,
Well, think back to the kinetic traps and the structural defects in the crystal lattice we discussed earlier.
right, the messy atomic musical chairs.
Exactly. When a localized region of the solar nebula is hit by a shockwave, the temperature spikes, vaporizing everything, then it plunges exponentially faster than equilibrium models account for.
So the temperature drops before the gaseous oxygen even has a chance to migrate away or form stable carbon monoxide.
Yes. The oxygen is caught in the sudden freeze. And because the cooling is so extreme, the solidifying non-volatile elements, the iron, the silicon, they do not have time to form those perfect, tight, crystalline structures that normally exclude outside elements.
Oh, wow.
They form messy, transient lattices full of defects, so the oxygen remains chemically available just long enough to get trapped directly into those higher energy structural defects as the solid grains are rapidly assembling.
The oxygen is literally locked into the flaws of the rapidly freezing rock.
Exactly. This kinetic trapping provides a totally natural, built-in pathway for incorporating oxygen into planetary materials right from the very first moments of condensation.
That is incredible.
We do not require an outside bombardment of comets to explain our oxidized rocks anymore. The violent, flash-freezing nature of the early protoplanetary disk intrinsically binds the life-giving elements into the structural flaws of the planet's fundamental building blocks.
Taking a breath of air takes on a completely different weight when you realize those oxygen molecules are chemically available to you simply because of a sudden, violent temperature drop billions of years ago.
It really does change your perspective.
It reframes the entire timeline of Earth's habitability. The conditions for life were baked in at the atomic level before the planet even fully assembled.
And the best part is, the Nature paper doesn't ask us to simply take their computer models on faith here.
Oh, right, the observational evidence.
Yeah, we are not just relying on the chemical analysis of ancient meteorites to verify this out-of-equilibrium chaos. We can actually look out into the galaxy and watch this exact kinetic trapping happen in real time.
This bridges the gap perfectly between ancient history and active astrophysics.
Mm.
The source material references the James Webb Space Telescope for this, right? Specifically, there's an observation of a young star system known as protostar L5327. And I have to say, the visual data here is stunning.
It is gorgeous. JWST has totally revolutionized our ability to peer through the dense molecular clouds where star formation is actively occurring. And protostar L5527 is a very young system, providing a direct analog to our own solar system during its first 100,000 years.
I am looking at the JWST image right now, and it looks like this massive, glowing cosmic hourglass.
Mm-hmm.
There's a brilliant, fiery orange cloud expanding upward, and a deep blue cloud expanding downward. And right at the pinch of the hourglass, cutting horizontally right across the light, is this stark, dark line. What exactly are we looking at there?
So that dark horizontal line is the protoplanetary disk seen edge on.
Okay.
It is an active, swirling accretion disk of gas and dust feeding the central protostar. And the massive hourglass clouds above and below it, those are outflow cavities. They're created as the protostar violently ejects material and magnetic energy outward.
Got it. So when astronomers peer into disks like the one bisecting L1527, they aren't observing a calm, uniformly cooling slow cooker.
No, not at all. They are observing pure dynamic violence. The JWST data proves definitively that the intense heating and rapid cooling described in the Nature study is a frequent, observable phenomenon.
We can literally see it happening.
Exactly. We see the shock waves tearing through the gas. We observe the magnetic turbulence causing sudden spikes in temperature, followed by rapid cooling in the outer edges of the disk. The out-of-equilibrium condensation that forged our planetary building blocks is not some localized anomaly. It is the standard operating procedure for star systems across the entire universe.
Which triggers a massive paradigm shift in how we categorize exoplanets.
A huge one.
Because, for the longest time, astrobiology has basically operated on the zip code theory.
Right. Location, location, location.
Exactly. A planet's composition, whether it is a rocky terrestrial world, a gas giant, or an ice ball, it was thought to be primarily dictated by its distance from the host star.
The traditional equilibrium models relied almost exclusively on that spatial location. The closer to the star, the hotter the slow cooker. The further away, the cooler.
It makes logical sense.
Sure. But this new framework proves that a planet's structural destiny is actually governed by localized transient dynamics. Its chemical makeup depends heavily on the specific chaotic rhythm of the heating and cooling episodes it experiences during its foundational moments.
So the rhythm of the flash freezing dictates the chemistry, not just the distance from the sun.
Exactly. Two planets could theoretically form at the exact same orbital distance from two identical stars. But if one protoplanetary disk experiences a different frequency of shock waves, or maybe a slightly different intensity of magnetic reconnection, those two planets will end up with vastly different atomic structures.
Wow.
One might successfully trap oxygen in the defects of its crystal lattice, while the other solidifies just slowly enough to let all those volatile elements escape, resulting in a dead, completely dry rock.
That just rewrites the rules of the universe, honestly. So to kind of synthesize this whole journey we have been on today, we started with the classical assumption that our solid world was born from a slow, highly ordered condensation process, a thermodynamic slow cooker.
A mathematical ideal that completely failed to explain the messy, diverse chemical reality of the non-volatile elements found in chondrite meteorites.
Right. The rocks forced the researchers to abandon equilibrium and embrace a model of violent, out-of-equilibrium chaos. Shockwaves and flash freezing, creating kinetic traps at the atomic level.
A localized, turbulent environment that perfectly reproduces the exact chemical profiles of the three major meteorite assemblages surviving in our solar system today.
And crucially, that exact same mechanism, the sudden, violent plunge in temperature, is what prevented gaseous oxygen from escaping, trapping it into the flawed crystal lattices of the very first rocks. The habitability of Earth is a direct product of that flash-freezing chaos.
And it's all validated by the active, turbulent accretion disks we can observe right now through the James Webb Space Telescope. It is a profound evolution in cosmochemistry, identifying a flaw in a foundational assumption, following the physical evidence of the rocks, and arriving at a more complex, dynamic understanding of planetary formation.
As we wrap up our analysis of this nature study, I know you always look for the broader implication. What is the lingering question this leaves us with?
Well, if the precise chemical makeup of a planet, specifically its ability to lock in the oxygen and volatile elements necessary to support life, relies so heavily on these chaotic, hyperlocal kinetic traps, well, what does that mean for our ongoing search for other Earths?
Yeah, because we filter our search for exoplanets almost entirely through the lens of the habitable zone, assuming that finding a rocky planet at the correct orbital distance is the absolute key to finding life.
But if this out-of-equilibrium model holds true, a planet's zip code is only a fraction of the story. Are habitable worlds a reliable product of predictable planetary real estate? Or are they the incredibly fortunate result of a highly specific, very chaotic cosmic weather forecast during their first 100,000 years of existence?
So if the rhythm of the shockwaves is off by just a fraction, or if the temperature doesn't plunge quite fast enough to create those structural defects in the rock, The oxygen escapes, and you get a barren wasteland instead of a living ecosystem.
It suggests that the existence of a highly oxidized, habitable world like our own might be infinitely more fragile and far more reliant on the precise timing of ancient violence than we ever realized.
Well, the next time you look down at the solid ground beneath your feet, remember that you aren't just standing on cold rock. You are standing on frozen chaos. You are supported by the surviving, flawed, structural masterpieces of a violent cosmic storm that just happened to flash freeze at the exact right atomic moment. Thank you for joining us on this deep dive into the true origins of our planet. Keep questioning the ground you walk on and keep questioning the universe around you.